Who hasn't heard or sung these words? While this poem is only 200 years old, but stars and skies have made humanity wonder since time immemorial. It's not surprising that for scientific community too, stars and skies offer an unusual laboratory. Indian scientist S. Chandrasekhar also got captivated with the mysteries of stars, and that ultimately made him become a permanent star on the horizons of astrophysics. Modern science has witnessed many outstanding scientists who revolutionized the human understanding of nature. Chandrasekhar surely is one of the foremost among them. With his prolific contributions to wide-ranging fields in physics, astrophysics and applied mathematics, he became a legendary figure. He has undoubtedly left behind a rich legacy of scientific accomplishments. Chandra lived on Earth and worked in space. Now, before moving to his scientific achievements, here are the glimpses of his early life. He was born into a Tamil-speaking family in Lahore in 1910. His father was a civil servant with Indian Railways. Mother Sita Lakshmi too was an outstanding lady. One can imagine, with only a few years of her formal education, she translated Ibsen's Dollhouse and Tolstoy's War and Peace into Tamil, which are still very popular.
Right from the age of 10, his mother had inculcated this kind of thing in him. Later on, when he was in his teens, I'm told that, when he was with his brother on the beach, he said, "Oh God, make me like Newton." So by then his icon was also Newton, and Newton remained his icon for the rest of his life.
As it is said, mothers are the first teachers. Chandrasekhar's education began at home with his mother Sita Lakshmi giving instructions in Tamil, while his father C.S. Iyer taught him English and arithmetic. In 1918, family moved to Madras, now Chennai. Here, Chandrasekhar attended the Hindu High School in Triplicane during the years 1922 to 1925. For his bachelor's degree, he joined Presidency College in 1925. Here, he studied physics, arithmetic, chemistry, Sanskrit, and English. From his early age, he had a liking for physics and mathematics. He also enjoyed English literature. In fact, his fascination with English literature contributed to his own lucid and impeccable writing style. Chandra was inspired by the mathematical accomplishments of great Indian mathematician S. Ramanujan, even before the college days.
When he was 10, and this left a huge impact on him, his mother read in the papers about Ramanujan's death, and she told him that a very big mathematician, Indian mathematician, has died. From that day, he had this thing of Ramanujan being an idol, sort of, an icon for him.
Chandra was more inclined to take mathematics honors. However, his father wanted him to become a civil servant and thought mathematics may not be a good option for that. Mother Sita Lakshmi supported Chandrasekhar, for she believed that one does best what one really likes to do. Ultimately, Chandra followed his father's desires and opted for physics. His father was more than happy as Chandrasekhar's paternal uncle, the Nobel laureate Sir C.V. Raman was definitely a great example to emulate. Hereon, Chandrasekhar launched himself into an intensive study of the quantum mechanics and statistics and wrote his first professional research paper, The Compton Scattering and the New Statistics. In January 1929, he communicated his work to Professor R.H. Fowler at Cambridge for publication in the Proceedings of the Royal Society of London. Fowler perceived the merit of Chandra's paper and passed it to the Royal Society. Getting in contact with Fowler played a very crucial role a year later when Chandra arrived in England. It was the year 1930. In final examinations at Presidency College, Chandrasekhar scored all-time high and Government of India offered him a special scholarship to pursue study and research in England for 3 years. When it comes to his style of research, it was his single-minded pursuit of science what made him so special. It so happened that on July 31st, 1930, on his maiden voyage to England, Chandra boarded a ship from Bombay. On the ship, he used to spend his time on shipboard, working out the statistical mechanics of the degenerate electron in white dwarf stars, which later came to be known as the Chandrasekhar limit. That time, Chandra was just 19 years old when he made this discovery, for which he was later awarded the Nobel Prize. Now, before digging deep into what actually Chandrasekhar limit is, it would be good to know a bit about the very existence of stars. Today, when we glance at the night sky, we see thousands of stars. These stars are older than human civilization. Stars started forming after about a few billions of years since the universe began. Look at these cosmic clouds. These clouds are called nebula. Nebula is a Latin word for cloud. A star is born in these huge clouds of gas and dust. These nebulae contain molecular hydrogen gas as well as other molecules like carbon monoxides, etc. It so happens that over millions of years of time, the turbulence deep within these clouds led to gas and dust collapsing under their own gravitational weight. Now part of the nebula begins to shrink gravitationally and an incipient star begins to take shape. For common understanding, life of a star can be compared with the human life, like fetus stage, childhood and adulthood. A star's formative state is like a fetus in an embryo. At this stage, gas density increases in the central regions due to gravitational contraction and the center starts forming. The central region is known as core of the star. Stars have huge masses which are measured in terms of solar mass, and they come in various sizes. But a gas cloud with mass less than 0.08 solar mass doesn't become a star. Such failed stars are called brown dwarfs. Stars, like human beings, pass through childhood, adulthood, and finally reach old age. The only difference is that at times most stars, like humans, don't die after the old age. Instead, they just settle in the background of the universe, growing colder day by day. Sufficiently massive stars have catastrophic end. They blow themselves up in the form of supernova. This middle stage of life, which ranges from its birth to the entire adulthood, is about 90% of the lifespan of a star. This period is known as the main sequence stage of a star. During the main sequence period, 4 hydrogen nuclei fuse to become helium, releasing a huge amount of heat energy. Of course, in normal situation, this would not happen. But unimaginably high temperature in the stellar core strips hydrogen atoms of their electrons to give rise to naked protons. And when the protons get close enough, nuclear fusion takes over, leading to formation of helium nuclei. The helium nucleus made by fusion is heavier than either of the starting protons. However, it is not as heavy as the combination of the original mass of the starting nuclei. This lost inertial mass appears as heat energy because of Einstein's famous equation E is equal to mc square. Nuclear fusion is a process in which 2 or more nuclei combine to produce a heavier nucleus. Stars shine brightly because of thermonuclear fusion taking place in their hot core. Main sequence stars are fueled by the nuclear fusion of hydrogen nuclei to form helium deep in their interiors. The outflow of energy from the central regions of the star provides the pressure necessary to keep the star from collapsing under its own gravity. As the time goes by, lots and lots of hydrogen in the core of the star combines to become helium. What happens when not much hydrogen is left in the core? Let's take a closer look at the stage when hydrogen in the core is depleted. Obviously, rate of nuclear fusion taking place gets reduced and heat production slows down. Once the nuclear reaction ceases, the star is deprived of the energy production needed to support it against gravity. The core begins to contract into itself and becomes much hotter. But hydrogen is still available outside the core. So hydrogen fusion continues in a shell surrounding the core. The increasingly hot core and fusion in the shell pushes the outer layers of the star outward, causing them to expand and cool, transforming the star into a red giant. The star is now very big. A star like our Sun, when it becomes a red giant, it will expand so much that it will swallow Mercury, Venus, and will reach almost the orbit of Earth. Now, due to this expansion, the gravity at the outer layers would surely weaken, resulting in leaking away of matter from the topmost layer into space, while the outer layer is exploding. What happens to the core? When hydrogen is depleted, not enough thermonuclear energy is generated, so pressure is insufficient to stall the gravity. The core will shrink in size. And when the core shrinks in size, once again, pressure and temperature increase. With a hotter core, the helium nuclei fuse to produce carbon and oxygen nuclei. When the core becomes carbon-oxygen rich, again, the nuclear fusion stops in low-mass stars, since temperature is insufficient to ignite carbon fusion. When the whole off core is almost carbon, this star is called white dwarf for forever. In white dwarfs, can there be further nuclear fusion and change of state? Chandra found that if the mass of the core is less than 1.4 solar mass, then the star would remain as white dwarf. This limit is called Chandrasekhar limit. All the white dwarfs discovered so far have masses less than the Chandrasekhar limit, vindicating Chandrasekhar's prediction. Eventually, after billions and even trillions of years, the white dwarf with mass less than the Chandrasekhar limit will cool down to the background temperature of the universe. As we experience that any hot substance over time cools down to the room temperature. Same happens with the white dwarf, and they attain the temperature of the universe, which is slightly less than 3 degrees above absolute zero at the present moment. When our Sun becomes a white dwarf, it will shrink to the size of Earth. But it will be extremely dense and massive. In general, when a star becomes a white dwarf, its core gets compact, shrinking to a size of about 10,000 kilometers. Their average density is about 1 million times denser than the density of the Sun. It's so dense that a single sugar cube sized amount of white dwarf would weigh about 1 ton. Now, why this limit is of 1.4 solar mass, and what will happen when it is more than 1.4 solar mass?
So what is this whole business of Chandrasekhar mass limit of white dwarfs? To understand that, we have to ask a particular question, and that question is, how does Earth stop itself from collapsing because of its own weight? We know that Earth is roughly a spherical body rotating about its axis.
We also know that any object which has mass undergoes a gravitational contraction because of the gravitational force. Imagine we take a small slab inside the Earth. Now, what forces are acting on this portion? Clearly, there is gravitational attraction on this element. If the gravitational attraction was the only force acting on this slab, it would have gone towards the center.
But the fact that Earth is not collapsing, there must be a reason why any part of the Earth is not collapsing under its own weight. And the reason is pressure. What happens is, if you take any slab inside the Earth, then the pressure on the lower surface is greater than the pressure on the upper surface.
This difference is acting in the upward direction and balances the gravitational force in a downward direction. Now, because of this, the Earth is in hydrostatic equilibrium and it is not collapsing under its own weight.
Why is the pressure on the lower part higher than the pressure on the upper part? And that reason is that the temperature in the downward part of the slab is greater than the temperature on the top part. We know from kinetic theory of gases that the pressure, temperature, etc. is because of the random motion of gas particles. Higher the random motion, higher is the pressure and higher is the temperature. So the random motion or heat or temperature on the lower part is higher than the random motion on the upper surface. The same thing happens for any star. Now, I discussed about Earth, but you can extend this argument to the Sun. Sun is a star, and why is Sun not contracting under gravitational force? The reason is exactly the same. After all, what is happening in the core of the Sun, what is happening is 4 hydrogen atoms fuse because of nuclear fusion to 1 helium nucleus. And the mass of the helium nucleus is less than 4 times mass of the hydrogen nucleus, and therefore because of the conservation of energy, mass energy, there will be energy liberated. And this energy essentially heats up the core, and the heat slowly diffuses outwards and the entire sun becomes hot. The regions closer to the center of the sun, it is hotter than the region outwards. And again, by the same argument, more the temperature, more is the pressure in regions closer to the center compared to the region outwards, and therefore this pressure difference, it balances the gravitational force which is acting in the downward direction. As the hydrogen nuclei fuse to form helium, the helium will also undergo fusion to form higher elements like carbon, nitrogen, oxygen. Eventually what happens is that the core becomes iron rich. Once the core becomes iron rich, the nuclear fusion shuts down. There is no more energy liberated. If there is no more energy liberated, then how does the core of the star maintain pressure support against gravitational contraction? Because the core eventually will cool down. Once it becomes cold, then the random motion will not be able to support the gravitational attraction. But does it mean that that's the end of the star? The core keeps on contracting and that's it? The answer is no. There is something called electron degeneracy pressure. According to Pauli exclusion principle,
gas is degenerate when all the particles within the gas are packed densely and the self-gravity is counteracted by pressure arising from Pauli's exclusion principle. Pauli's exclusion principle says that no two identical spin half particles can have exactly same quantum states. This basically means that no two identical spin half particles can be at the same place at the same time with spin pointing in the same direction. Pauli's exclusion principle does not favor increase in density. In white dwarfs, electrons become degenerate, while in neutron stars, neutrons are degenerate. A star with initial mass less than 8 solar mass becomes a carbon-oxygen white dwarf with gravity counteracted by electron degeneracy pressure. A star with an initial mass greater than 8 solar mass evolves into an iron-rich core, after which nuclear fusion shuts down. Now the core contracts and the iron nuclei are crushed further and they turn into neutron-rich matter. If the degenerate neutron-rich core is less than 2 to 3 solar masses, the core becomes a neutron star. This is a kind of Chandrasekhar limit for neutron stars.
That for white dwarf, the degeneracy pressure is proportional to the density to the power 5/3. Chandrasekhar was the first person to realize that in the iron core inside the white dwarf, most of the electrons are actually moving with speed close to the speed of light. Of course, nothing can move faster than the speed of light, but what Chandrasekhar realized are these electrons are moving with speeds close to the speed of light. But once you have electrons moving with speed close to the speed of light, then new effects come in, that means relativistic effects come in, and that makes the grow not as density to the power 5/3 but density to the power 4/3.
In fact, the Pauli's exclusion principle of quantum mechanics restricts the number of electrons that can occupy any energy level. This, along with relativity, lead to Chandrasekhar limit. Einstein's theory of relativity predicts many strange effects. One is that when an object's speed changes, so does its mass. For example, if it were possible to weigh a person traveling at 90% speed of the light relative to a stationary person, he or she would weigh far more than normal. But to them in their rest frame, however, everything would seem normal. It is this feature that leads to the famous E is equal to mc square formula. Now what happens if the mass of a white dwarf increases to more than 1.4 solar mass? In 1987, in the Magellanic Cloud, a star burst into a supernova. Today, we call this star as SN 1987A. This star was visible for many days, even during the daytime. If you have a binary star system with one of its members being a white dwarf, then matter from the other star can seep onto the white dwarf. This slowly starts increasing the mass of the white dwarf, causing increase in its mass beyond 1.4 solar mass after some time. Until now, in the white dwarf, the gravitational force and electron degeneracy pressure were acting in opposite directions, and the star was stable. However, when the mass from the companion star gets added to the white dwarf, the gravitational force becomes stronger, overcoming the electron degeneracy pressure. According to Chandrasekhar limit, the star is no more stable and it explodes as type 1a supernova. By now, hundreds of types of supernova have been observed, which goes on to prove that Chandrasekhar was absolutely right. Coming back to Chandrasekhar, he was so sure of his finding that while talking about the same during a conversation with Kameshwar C. Wali, professor of physics at Syracuse University, New York, Chandrasekhar said that, "After all, I was in my middle 20s at that time, and I foresaw for myself some 30 to 40 years of scientific work, and I simply did not think it was productive to constantly harp on something which was done. It was much better for me to change the field of interest and go into something else. If I was right, then it would be known as right. For myself, I was positive that a fact of such clear significance for evolution of the stars would in time be established or disproved. I didn't see that I had the need to stay there, so I just left it." Consequences of Chandra's first research paper were more far-reaching than anyone could have imagined. He took up his studies at Cambridge and spent a lonely but productive year in intensive study and research. Further, death of Mother Sita Lakshmi in 1931 added grief to his loneliness. At Cambridge, Chandrasekhar continued his work on atomic absorption coefficients and mean opacities, but with a growing sense of frustration from his feeling that he was abandoning mathematics through his pursuit of physics and abandoning pure physics through his pursuit of astrophysics. Further, Chandrasekhar's feeling of frustration with his peripheral science led to his spending his third year at Bohr's Institute in Copenhagen. Developments here convinced him that his real strength lay in developing and expounding the implications of the basic physical laws of nature, as distinct from the pursuit of new laws of nature. Chandrasekhar finished the year with 4 papers on rotating self-gravitating polytropes, which became his PhD thesis. His government scholarship ran out. Fortunately, he won one of the highly competitive appointments as a Fellow of Trinity College, which ran for 4 years. He was nominated as the Fellow of the Royal Astronomical Society, and the future was clear for the immediate years at Cambridge. A new development took as Hal Shapley invited Chandra to visit the Harvard Observatory. Chandra arrived in Boston on December 8, 1935. Otto Struve invited Chandrasekhar to visit the Yerkes Observatory of the University of Chicago. Back home, other than his family members in India, Chandrasekhar used to communicate with Lalitha Doraiswamy, who had been a fellow student in physics at Presidency College. He came to India for a visit in August 1936 and wrote to Lalitha that he would be at Madras. They were married on September 11, 1936.
He and my aunt actually met in college. She was a year junior to him, but they had some classes in common. Friendship grew from there. He went away to Cambridge, came back after 6 years, and then he got married to her. And he always said that, I met a girl who waited for me 6 years. I came back and married her, and we lived happily ever after. That is the story of my life. In those days, it was not the usual thing to have a love marriage. They got married in 1936.
The University of Chicago provided Chandrasekhar with his scientific home for the next 59 years. Enrico Fermi invited him to become a member of the Department of Physics and the Institute of Nuclear Studies, now the Enrico Fermi Institute. Chandrasekhar accepted the invitation. Here, an interesting incident happened with him, for he is the only professor whose one of the entire class got the Nobel Prize. This story is very popular among the scientists world over. The story is, one day there was a huge storm in Chicago. Nothing was moving on the road, and Chandra had to drive down 50 miles to take the class. Now, irrespective of difficulties, Chandra's commitments to science were intact. He drove to the class, and that day, because of storm, only 2 students, Sung Dao Lee and Chen Nin Yang, could make it to the class. It so happened that both Lee and Yang got the Nobel Prize in Physics.
He understood that many universities in India did not have the necessary infrastructure which students needed in terms of books in the library or access to journals and things like that. But he always felt that the onus was still on the student, and if a student really wanted, he could have access to those things, because there were places where they were available. They could write to people where they were available. He said there are so many things, once the net had come, that so many things are available on the net, and there are many people who would be willing to help you, but you have to approach them instead of just saying that, oh, this is not available to me and so I can't do anything. So his attitude was always not to accept that circumstances or infrastructure is restricting you to do something. It is how much passion and thing that you have that drives you, and you will find your way and you will find the things that you need if you really are set up to do that.
In 1964, Chandrasekhar moved permanently to the Chicago campus. The transition was catalyzed by John Simpson's offer of a spacious corner office in the newly constructed laboratory for astrophysics and space research. Honoring this great scholar, today this laboratory has a telescope named after him, known as Chandra X-ray Telescope. Here only, Chandra took up the onerous task of managing editor of the Astrophysical Journal. Under Chandrasekhar's leadership, the journal developed into the leading international journal in astrophysics. In 1953, he became naturalized citizen of US, and citizenship led to Chandrasekhar getting elected to the National Academy of Sciences. The course of Chandrasekhar's research is perhaps best summarized by the monographs that he wrote as he completed each phase of his work. An Introduction to the Study of Stellar Structure, 1939. The Principles of Stellar Dynamics, 1943. Stochastic Problems in Physics and Astronomy, 1943. And Radiative Transfer, 1950. This book remains a classic to this day. His other books are on plasma physics, hydrodynamic and hydromagnetic stability, ellipsoidal figures of equilibrium, the mathematical theory of black holes, truth and beauty, aesthetics and motivations in science, Newton's Principia for the common reader. His life journey was full of accolades. Beginning with the Fellow of the Royal Society in 1944, he was honoured with Henry Norris Russell Lectureship in 1949, Bruce Medal in 1952, Gold Medal of the Royal Astronomical Society was given to him in 1953, and then came the National Medal of Science, USA, in 1966. And in 1968, he was honoured with the Padma Vibhushan, and that followed by Henry Draper Medal in 1971. The big one, the Nobel Prize in Physics, came in 1983. He was also accorded with Copley Medal of the Royal Society in 1984, Honorary Fellow of the International Academy of Science in 1988. His findings continue to inspire the scientists till date. Even Stephen Hawking, a living legend, has paid a huge tribute to Chandrasekhar in his book A Brief History of Time. Talking about Big Bang to black holes, in his book, Hawking explores the answers of big questions like where did we come from and why is the universe the way it is. This book has sold over 10 million copies. One can imagine the importance of Chandrasekhar's findings, for in A Brief History of Time, Stephen Hawking has named him over a dozen times. Chandra had a personality that has left indelible mark on each and everybody who met him. Among the Indian scientists too, he is revered. It is not surprising that even after his death, Indian scientific community loves to celebrate his works and life. Symposia and seminars in his memory are continued to be organized by the international as well as Indian scientific community.
So in 1946, Subramanian Chandrasekhar gave a talk here in Chicago with the title The Scientist. He was then 35 years old, less than halfway through his life, less than a third of the way through his career as a scientist, but he was already reflecting deeply on the meaning and purpose of his work. His talk was one of a series of public lectures organized by Robert Hutchins, then the Chancellor of the University. The list of speakers is impressive, including Frank Lloyd Wright, John von Neumann, Arnold Schoenberg, and Marc Chagall. That list proves two things. It shows that Hutchins was an impresario with remarkable powers of persuasion, and he already recognized Chandra as a world-class artist, whose medium happened to be theories of the universe rather than music or paint.
Chandrasekhar always commanded immense respect among the scientific community. Here is an example. Look at this watch. This watch belonged to Chandra, who later gifted it to her niece Radhika Ramnath. Here, this number 17 has a very special meaning, as it was article number 17 which was taken on the American Space Shuttle to honor Chandra for his contribution to science.
I got it. I got it.
Chandra was a lover of literature and was known for amazing writing skills. No matter it was a scientific paper or personal communication to friends and relatives.
My dear Radhika, you found time to write 3 letters while I have been negligent. Talking over the phone is a lazy person substitute. I was amused to hear about the escapades of the book I sent you. That they ended successfully is, as you say, heartwarming. The only news I have is that my book on the Principia is really finished.
His pen followed his minds with same clarity.
Oh, he was a great storyteller. I mean, he could remember, his memory was fabulous. So he would relate to you incidents which had happened about 50 years ago as though they had happened yesterday. So the way he told a story just brought it to life, you know. And for us, figures in, what shall I say, our science books, you know, Rutherford, Fermi, they were names. And then he would tell you incidents about them and they would all come back to life.
His interest outside the scientific world can be fathomed from his book, Truth and Beauty, published in 1987. It shows an entirely different side of his thinking. This book includes his Ryerson lecture, Shakespeare, Newton and Beethoven, in which he explored and compared the motivations and feelings involved in the creation of science and art. In 1995, Chandrasekhar's death brought an end to an unforgettable era, and that's the reason he continues to inspire the scientific minds even today. And what a tribute to this! His ashes were sprinkled all over the Chicago University campus.